So good evening everyone, or whatever time you're watching this. This is Psy234 part 3, and today we're talking about, I should make that bold, but that doesn't matter, factors that affect growth and development. So at the end of this lesson, as usual, you should understand the basics of meiotic cell division, understand how certain traits like eye color is passed down, know the specific traits or disorders determined by heredity, know the environmental conditions that influence or determine growth, know how urban and rural areas influence learning, and know how and where children are different. I said children's. Know how and where children are different. Alright, so this video might actually be a 2-part video because there's a part that I might need to really explain. And maybe to mitigate that, or to make it one video, I might skip unnecessary reading. Like hereditary mechanisms. When the sperm cell, I'm not reading all of that anymore. According to Thompson and Callis, every individual supply of genes and bearers of hereditary factors is given him or her once and for all in alternation at conception. Everything that you are going to have, everything you are going to be is already given to you at conception. So at conception, there are 23 pairs of chromosomes. 1 half from the father and 1 half from the mother, which makes it 46 chromosomes from both sides. 23 pairs means 46. So your father gives you 23 and your mother gives you 23. 46. These make up everything that determines the heredity of the child. Now, meiosis or meiotic cell division, production of gametes. Now, the normal body cell, somatic cells of an adult contain 23 pairs of chromosomes. 23 pairs. 23 pairs means 46 chromosomes. Don't let that confuse you. That's 2n. That's a diploid number. So 46 chromosomes or 23 pairs of chromosomes is what? A diploid number. If the egg cell and sperm cell of the parent should contain 2n chromosomes, that means if in the gamete, so in the egg cell and in the sperm cell, if both of them should hold if both of them should hold 46, that's 2n chromosomes, then an offspring will have 46 pairs. That's 46 plus 46, making 92. Yes. This will be bizarre. That will cause a problem. There is therefore a mechanism in nature to maintain the diploid condition in individuals. This is done through meiosis, a type of cell division which tends to divide an initial cell into halves, having half the number of the 23 pairs of chromosomes. These daughter cells, I don't understand what I read it, but these daughter cells have the haploid number. So 23 cells or 23 chromosomes is called what? A haploid. 23 plus 23, 2n, or a diploid, or 46 chromosomes is called a diploid. Okay. This type of cells with haploid number of chromosomes each are called germ cells or your gametes. So a man's gamete is the sperm and a woman's gamete is the ova or eggs. So this is 2n. So now they're trying to break it down from complex to simple. So this is 2n. To make that 2, you need n and n, haploid number. And the haploid number is what? 23. And 2n is the diploid number. That is massive. Now, meiotic cell divisions. Terms in genetic inheritance. So hereditary. Hereditary is the transmission of traits from parent to offspring. So all the traits of your physical, mental, and other characteristics is transferred from the parent to offspring. That's heredity. Now, chromosomes. Chromosomes are structures found in the nucleus of any cell on which genes are located. Again, chromosomes are structures found in the nucleus of any cell on which genes are located. Now, genes are the bearers of hereditary factors. These factors are the information for expression of characteristics which are passed from the parent through the gamete to the offspring. So basically, that's easy enough to understand. Genetic information are stored on genes of other structures called DNA. Whatever is the roots, whatever is the roots. DNA is the nature's code or blueprint for genetic makeup of each individual. If you have a little note, you can be writing all these things down. Just be writing all the key points, so you don't always have to open this thing. Now, So, inheritance of eye color. It has been found that whenever the gene for brown eyes is present in an individual, the color of his eyes or eyes will be brown even when other genes are present. So, meaning that the brown eye color is therefore said to be dominant to the genes for blue or green eyes, which are said to be recessive. Now, the gene for brown eye is represented by a capital letter B, and the gene for either blue or green eyes is represented by small letter b. I'm sure you already guessed it, but the dominant will always be represented by the capital letter, and the recessive will always be represented by the small letter, just to show you the difference. Now, dominant genes and capital letter. Okay. If a man with pure brown eyes, BB, marries a pure blue-eyed woman with small letter b's, then their offspring will all have brown eyes, as shown below. Now, do you know why there are two capital letter B's? Because this person is a pure brown. So two B's, two big B's, and we already know that the big B in this case is brown eyes, and this woman has two small letter B's, which already know that she is a pure blue-eyed person. So they try to draw a diagram here, but I think we can do it better. So here we have the eye color transfer. So the man is BB and the woman is small letter b. So now from the red, we can draw that this first one will be B and a small letter b. Then for the second one, that's for the yellow, which is B and B. I hope you understand. Small letter b, that's the yellow. So we can also say that is B. There's no way I can actually show you like my cursor. If I could, that would have been fantastic. Now the next one, the blue, so that would be B and B from the woman. So that would be big B and small b. Then the last one will be the green, so that would be B and B. I hope that's helpful, sir. B and B. So from this, we can draw some conclusions. We can see that every single child that they will make has the dominant B, meaning that every child they give birth to, or this pair of people will give birth to, even though the woman is a pure blue-eyed person, every child that they give birth to will have brown eyes, because the dominant trait of brown is on every child. So, and I hope this was a little bit more helpful than what they did. Now, when an organism contains identical genes, either big B's or small b's, it is said to be homozygous. When an organism contains two dissimilar genes, that's one big B and one small b, it is said to be heterozygous. Now, heterozygosity or homozygosity describes the genetic constitution of an organism, i.e. the type of genes it carries. Now, the genetic constitution, that means these BBs, all of this, the genetic constitution is called the genotype. And you having the brown eyes, like what they now later let you do, or what physically come out, are known as the phenotypes. You can read it there, it's on the page. Now, genotype for brown eyes is BB or BB, and the brown eyes is the phenotype. I'm sorry, it's just funny to me. Now, supposing a homozygous man-eyed BB marries a heterozygous brown-eyed woman, what offspring would they produce? Now, I think I made one for that too. So now, this is the man. And then this is the woman. So the man is a heterozygous. Why is he heterozygous? Because he's not pure black. So he has a recessive trait, which is the blue-eyed gene. Now, we can easily form, just to save time, I already done it for us. So now, the red, if you look at, we're taking the big B from the man, and we're taking the small b from the woman. Then we're going to do the yellow. I like doing like, never mind. So now we have the big B from the man for the yellow and the small b from the woman. Then the blue color, the small b from the man and the small b from the woman. And then the small b, that's the green, the small b from the man, and the small b from the woman, that's the green. Now we can also make some conclusions. Firstly, if you look at it, we can see 50% of all her children will have brown eyes. And then we can also see 50% are pure blue-eyed. Have pure blue eyes, rather. Have pure blue. Oh my God, what is happening? Pure blue eyes. So does that make any sense? Because this one is an heterozygous, and then the B is a dominant one. That means brown eyes is always dominant. So 50% of our children will always have, or will have, brown eyes, and 50% of our children will have will be purely blue-eyed. So I'm doing this because the exam can just come up and be like, oh, an heterozygous man married a homozygous woman. What would he form? I mean, what's the percent of our children that will have this? That's why I'm trying to show you what they can equate. So you can just make your not stories, but like you can make your conclusions up from this. So we're going to move on. Now, from the above, they will produce two heterozygous brown-eyed, and two blue-eyed, that BB. Now, specific trait determined by heredity. Now, this part is going to be talking simply about all the things that will be determined alone by heredity. So, environmental factors do not affect anything here. So, sex determination. The sex of the child is determined at the time of fertilization. Now, chromosomes produced by mature sperm cells from males either differ in character. These different chromosomes are the sex determinants. There are usually two types. The larger one is the X chromosome, and the smaller one, which is about 1/3, you can write that down, of the size of X chromosome is called Y chromosome. Now, that's serious. So, basically, you should already know this. Every woman has XX, and every man has XY. And if the sperm that unites with the ovum is the X type, then we have XX genotype. But if the Y-bearing sperm unites with the ovum, that means if the man gives out Y, then the child will be male. Then the production of a male child solely lies with the man. That the family produces female children consistently is therefore not the fault of the wife. So do you hear that? Don't chase the queen away. It's your fault. Diagrammatically, this can be okay. This one doesn't need that much. From what I just showed you before, you can draw it out. So the chances of having a male is 50%. The chances of having a female is 50%. So I don't think I really need to show you this. Also because I didn't make one for that. Twins development. A is usually brought about by development of two babies. There are usually two types of twins, identical and non-identical. So non-identical, the woman normally has two ovaries with the possibility of releasing two eggs. So that means in this case, the woman released two eggs, and the two eggs were fertilized by two different sperm cells. Those two embryos will eventually lead to the birth of two non-identical twins. Now, these fraternal twins will look just a little alike, and they may be of different sexes. So often, dizygotic twins, another name for non-identical twins is called dizygotic twins, remain different in every way till adulthood. This difference may be magnified by environment. Magnified by environment is if the environment are drastically different, the children will be even more different. Now, identical twins, this one is in a case where one sperm cell fertilizes one egg, but that egg divides into two, making a monozygotic twin. So any difference between them is accounted for by the environment in which they develop. That identical twins have different personalities caused by the environment. It's caused by the environmental factors. Now, specific traits determined by heredity. Okay, just going to continue on that. Now, we have already said that it's difficult to determine what trait heredity endows that are not influenced by the environment. However, there are some that must be mentioned. So, physical features. It is easy to see that children are very often to their parents. We do not mean that they're exactly alike, as we have just learned they inherit from both father and mother. So, intelligence too is also inherited somehow. Disorders are also inherited, are also inherited from your parents. Now, the commonest form of inheritable sickness in our environment is sickle cell anemia. People should know more about how this condition is inherited. Unfortunately, we cannot go into it now. Well, other forms of disorders and disease are also inheritable. So the rate of development, the rate at which you grow, or the rate at which you grow will be different from the rate at which someone else will grow. No matter if you put them in the same environment, their rate of growth will still be different because it is in their hereditary. I don't know why I keep saying hereditary. Now, blood type. People normally say blood is thicker than water. Perhaps you say that a child always inherits the blood type of his parents. So that is great. The status of individuals with respect to genetic disorders. Okay. Different genes affect individuals in different ways. That is crazy. A person may have a gene for a particular genetic disorder but be asymptomatic, either because the onset of the disease will occur later in life, e.g. Huntington disease, or because the disease is under control, hemochromatosis. That's crazy. Some genes make it virtually inevitable that an individual will eventually show the symptoms of the disease, Huntington disease, whereas other genes merely make an individual more susceptible to developing a disease. So that means some genes will give you some disease eventually, and some will make you susceptible or easier for you to get some diseases later in life. So heart disease and late onset Alzheimer's disease. An individual may be a carrier of a genetic disorder, that is, have one copy of a gene associated with a recessive genetic disorder and one copy of its normal counterpart. This meaning that someone can be a carrier. And when you are a carrier, meaning that the gene of the disease is recessive and you have a dominant normal gene. So that means it will not show on your body. You'll be asymptomatic. All you can do is pass it on from you to your child. And if you marry someone that also has that gene as recessive or dominant, there's a very high, almost surely that you will create a child that has that disease. Now, types of genetic disorders and patterns. A human being has 23 chromosomes. One member of each pair is received from the father and the other from the mother. Chromosomes carry genes. Genes are composed of DNA pairs which work through coding for the production of proteins. Now, chromosomal disorders arise from errors in the packaging of genetic material. Now, this is either caused by too much chromosomal material or too little. The chromosomal material has been misplaced or rearranged or mutated. In a few cases, these disorders are inherited. So in a few cases, these disorders are inherited from one of the parents who is a carrier, but in vast majority of the cell, they arise when a defective germ cell is produced or when the cell is subjected to some change. Now, we have some chromosomal abnormalities. For example, the Klinefelter syndrome. The male child has an extra X chromosome, so that means the child is XXY. It affects males, and affected males are infertile, have small testes, and poorly developed secondary sex characteristics. So I'm guessing your testosterone is low. And may be tall and have subnormal intelligence. A child with trisomy 13 usually dies shortly after birth. That's an extra chromosome number 13. So trisomy 21 will be an extra chromosome number 21, and this is Down syndrome. So now we have autosomal dominant. An autosomal dominant disorder occurs when an abnormality in one pair of a gene is sufficient to cause the defect to appear. Meaning that you don't need it to be pure, or you don't need the gene to be homozygous in nature. So you just need it. So autosomal dominant just means that once one of it is there, you'd be symptomatic. You'd have that disease immediately. So autosomal dominant disease include Huntington disease, whose symptoms of uncontrolled muscular movement appear about age 35 and progress through neurological degeneration, including dementia till death, over a 10 to 20 year span. Then we have neurofibromatosis. Then we also have skin tumors, which are often benign meaning non-cancerous, and some skeletal changes. Then we also have polycystic kidney disease, which is the formation of cysts in the kidney. So I think I have something for that. Now, I don't know if this stuff is actually helping out, and also for this paper and this paper alone, we're going to call this A the normal and this A asterisk the disorder. So A is normal gene, and then A asterisk is like the disorder or the Huntington disease. Now, autosomal dominant is saying if just one of the gene is present, the child will have it. So now, if these people, they should make children, their children will look like normal, that's AA normal, then A asterisk, then AA asterisk, AA asterisk. Meaning that we can draw some conclusions from this. Meaning that 50% of their children will have the disease. Now, why do they have this disease? Because it is autosomal dominant. You don't need the two. For blue eyes and the color and stuff, you needed the two to be small b's for it to work. But in this one, it doesn't care if it is one or if it is two. Once you have the trait, or once you have this gene, you're going to have the disease. You're going to be symptomatic immediately. I hope that helps a little bit. Now, then we have autosomal recessive. Now, this one is a disorder. It's caused by abnormalities in both members of a pair of genes. Lol. Both parents may carry a single dose of the gene on one chromosome but have a normal gene on the other chromosome, which prevents the appearance of the disease in the carrier parent. A child must get one abnormal gene from each parent in order to be affected by the gene. Now, there's another diagram for that. Now, in the same scenario, now this one is recessive. A is normal, A asterisk is abnormal, or the disorder. Now, can you tell me, from what you can see, oh, it's not an interactive class. I know it's not an interactive class. Shut up. Can you tell me, or do you know which one is? How many children will have a disease? None of the children will have a disease. Because why? There is no single pair that is complete. For an autosomal recessive disorder to take effect, or to cause symptoms in your body, it needs to be complete. It needs to be that both your parents have given you this disease. So none of the children in this case. But if, for example, let's say this mom has, or this dad has has another one. So what is now going to happen? This red, there's going to be a lot of changes. So now this is going to be like A star. Then this two is also going to be A star. Then for the blue, it's almost going to be the same thing. So it's more of actually the same thing now. But now we can say that 100%. So now all of them are the same thing. But now we can say that 100% of the children are carriers. of the disease. I hope that makes sense. So if someone that is pure or that has normal genes marries someone that is defective or has the full disease, if the disease is autosomal, if the disease is an autosomal recessive disease, there's no risk of the child being born with the disease, but all of the children will be carriers of that disease. I hope that makes sense. I feel like I've taken too much time. Examples of autosomal recessive disorders are PKU, an error of metabolism which can result in mental retardation, growth disturbance, and eczema if not treated with a special diet. All these things, again, you can write them down because you can just ask, is PKU an autosomal or recessive? Or is it a recessive or a dominant? Then we have Tay-Sachs disease, which causes progressive deterioration and death in early childhood. Then we have cystic fibrosis. So let's read. Parents who are both carriers of autosomal recessive disorder have a 25% risk of producing an offspring affected by the disease and 50% risk of producing normal appearing carriers. So parents who are both carriers. Now let's go and solve it again. Now this time they said parents who are both carriers, not parents that, or not one parent that had disease and one parent that doesn't. So a carrier here and a carrier here. Oh my gosh, it's taking so much time. So now we have A, for the red, we have A and A, the child will be normal. So this first child is going to be normal. Then for this and this child is going to have one A. Then for the blue, the child is going to have another A. Then for the green, the child is going to have the disease. So I don't know if this is helping at all, because it just feels like I'm saying this and this. So now the story is going to change, or the conclusion is going to change. Now we can say 25% will neither be a carrier or have disease. Because look at the person under the A, he has no disease or is not a carrier. Now we can also say, according to the book said this. Now we can also say 50% will be a carrier of the autosomal recessive disease. Now 50% carrier. I'm just going to write carrier. Now we will know for sure that the other 25%, or the last 25%, that means 1 out of every 4 children that she has, will definitely have the disease. I hope this makes any sense at all. And if it doesn't make sense, that's tough. Now we have X-linked recessive disorder. X-linked recessive disorder is a disorder that is happening on the X. I don't know if... Okay, X chromosome. Now, an X-linked recessive disorder occurs when the abnormal gene is carried on the X chromosome. Now, a female with an abnormal gene on one chromosome will usually not have symptoms because of the normal partner gene on the other X. You know, women have XX. So, why it is recessive... women have XX, so it will not show on them, because even if one has the disease, the other one will not show. She has another X, so making like it will count out, or it will cancel out rather. On the other hand, if a gene on the X of the male is abnormal, because there is no partner gene on the Y to compensate, the symptoms of the disorder will occur. Now, I hope that makes sense. So in X, why this one is called recessive is because in the female, if she has, because in every woman, the woman here can only be a carrier. So because she has the other X that is good, she wouldn't show any symptoms. But because the guy or the male doesn't have any other Y to compensate, he's going to show symptoms. Now, I think there's X-linked recessive. Let's start with woman. X-linked recessive woman. Now, from here, you can see that this is the woman XX and this is the man XY. So now to form this out, I thought I written this out. So now they're going to give birth to, now look at it. This woman, meaning that is the woman that has the disease. And now they want to make children. So meaning that they will have XX. Meaning that they will have XX. What is under the yellow? X and Y. They will have a regular boy. Then under the blue, what is there? They have the X-linked recessive disorder. That's the X. That is under the blue. Then they will have a girl. X. And the X, this girl is going to be a carrier. And then under the green, they are going to have a boy who definitely has the disease. You know why he's going to have the disease? Is going to have the disease. Now, if we look at this, we can draw some conclusions. Now, in the exam, they can be like, oh, in X-linked recessive, if the woman has the X-linked recessive and she marries a man, what is the percentage of what's the percentage of children that will have this disease, or what's the percentage of children that will be a carrier? So now we can tell that 50% of our children will either be a carrier or have the disease. We shall have the traits in them, and 50% of them will be regular. So meaning, and if we want to break it down before that, we can say 25%. Sorry, we can say 50% of the girls will be a carrier. So look at now, we have 2x. So half of them will always be a carrier, and 50% of the boys will have the disease. Hope that makes sense. So look at it one more time before we go back. Now, a carrier female has a 50% chance of producing a son affected with the disease, and a 50% chance of producing a daughter who will be a carrier. And we just solved it out. So after the X-linked recessive in woman, we're also going to talk about the X-linked recessive in man. So let's see what happens if the man has the X-link. So now, under the red of recessive, so under the red, we can tell that X is the woman. So that means this first child is definitely not first child, but this child under here will be a carrier. So the first, or the female will be a carrier. So under yellow, we can tell that XY, the boy will be regular. Then under blue, we can tell that blue, it will be a carrier, X. Then under green, we can tell that it will be a regular boy, X, Y. So I think this is some good news. So if the man has an X-linked recessive disorder, all of his female will be carriers and all of his boys will be healthy. See? So now it can be different. So now they can just spring up that question for you. So 100% of his boys will be healthy, and 100% of his girls will be a carrier. My bad. Carrier. Hope that makes sense. If the man has an X-linked recessive disorder, you can make some, you can draw some conclusion. Now, the next thing is the X-linked dominant disorder. Now, this one, we've already learned about autosomal dominant disorder. So in this one, it's almost like that. So now, disorder, the abnormal gene is carried on an X chromosome of either male or female. So now, in this one, this child under the red is is just a carrier, she wouldn't have the disease. But in X-linked dominant, the child will, as long as it's there on you, the child will definitely have it. So the disorder, the abnormal gene is carried on an X chromosome of it. If the mother is the carrier, there's a 50% chance that the child will be born with the disorder. All daughters of an affected father will have the disease. I can show you both, but let me just show you the father. Maybe you can do that on an assignment by yourself. So X-linked dominant, where are you? No, that's woman. The X-linked. Oh my God, did I not? X-linked recessive man. X-linked recessive man. How many X-linked recessive man? So I'm guessing this is dominant. Now, for dominant, if the man has it, the book said all women, all of his daughters will definitely have the disease. Meaning that even if you just have one gene, you will have it. So now let's see why all his daughters have the disease. So this would be XX. Then under the yellow, that will be XY. Then under the blue, that will be X, X, X. And under the green, that will be XY, XY. So now, if you look at it, you can basically draw some conclusion. And if you are still confused why so now the conclusion we can see is 100% of his daughters have the disease. Now, that's fantastic. So if you don't, do you understand why all of them have the disease? Because this one is dominant. As long as you don't need the two for it to become dominant. You just need one. As long as you have one of these gene, you already have the disease. You're not a carrier. So, and for X-linked, if the woman is the one that has it. Now, for this one, if it's the woman that has it, I think it will be more spread out. Yeah, this is definitely going to be a 2-part video. So this will be X under the other X. This will be XX. If it is the woman that has it, then this will be XY, healthy boy. XY. Then if it is, then under the blue, that will be an XY, X that has the disease, and Y. Then under the green, we have, sorry, this is XX. And under the green, we have X and Y. So now we can draw some conclusions. 50% of all children will have the disease if the woman is born. You can see it's very different. Now, 50% of children disease. Now, the other 50% will be safe. Now, you can also see 50% of the male child will be safe. 50% of the female child will be safe. Stuff like that. Now, I think we are going to stop here. But let me finish. If the mother is the carrier, there's a 50% chance that the child will be born with the disorder. All daughters of an affected father will have the disease of an X-linked dominant disorder. All daughters of an affected father will have the disease. All daughters of the affected father will have the disease. Look at, because it's dominant, you have X under the red and XX under the blue. Those are women. So 100% of all his fathers, of all his daughters will have this thing. Now, an example of X-linked dominant disorder is incontinentia pigmenti. Serious. Which brings about swells of pigment in the skin that resemble swells of paint or marble. This disease may also involve hair loss, visual problems, missing or peg-shaped teeth, and seizures. I think that is the end of all of the the XY, XX. So we can look at it again. Also, I think I missed something here under this X-linked. If a gene of the X chromosome of the male is abnormal, there is no partner gene for the X. Okay. Hence, X-linked disorders are carried by females, but primarily affect males. Such diseases are Duchenne muscular dystrophy, hemophilia, and some forms of growth hormone deficiency. A carrier female has a 50% chance of producing a son with disease and a 50% chance of producing a daughter who will be a carrier. Now, they said something here. Are carried by females but primarily affect males. I think we can also use the book or this to solve it. X-linked recessive woman. So now if you look at it, the girls have it, but the disease will not show in them because they are just carriers and they have another X to counteract it. Or to, then cancel it out. Then for the XY, since they don't have you need your two genes to be working well. You need X and Y. But if your X is fucked up, even if it's a recessive gene, nothing else to support it. You get? So that'll be X and Y. Then autosomal recessive disorder is saying you need like your both parents to deliver or to give you those two bad genes for you to get it. Let me show you the diagrams again. I just hope these diagrams are helping you out. Autosomal recessive. So if you look at it, you can see that only one child, because of the green, look at the green line, A star, A asterisk. Now for the purpose of this lecture, I've said it before, A asterisk or asterisk means that the disease and no asterisk means you are good. So 25 will neither be a carrier or have the disease. That's 25%. That means one of the children out of 4 will neither be a carrier nor have the disease. So I think I'm going to stop here for today. So I'll be for this first part. So just try to practice. There will be no questions, just practice. So just try everything. You can try A asterisk and A for the mom and A asterisk and A for the dad. See what it gives you. Or try everybody should have the disease. Just try whatever you want to try. So for this part, I'll just say you should practice. So in the second part of it, we will talk about these multifactorial disorders. We start from chromosomal abilities because multifactorial disorders is just a combination of disorders or combination of genes inherited from parents and environmental factors. So disorders you get from your parents and the environment. That's a terrible life. So we'll see you guys soon. Bye.